Hey guys, this video covers the review lecture for the second exam for Math 141. If you're taking my class, then I have a sheet of notes that comes with the exam. And so it has on it, we got all the properties of logarithms from 4.3 and 4.5. Continuous growth decay formula, so this is what we were using in 4.7 to do those application problems. And then from section 3.2, standard and vertex form with the definitions for quadratic and then quadratic formula. So that's all the stuff you don't have to memorize for the test. This will be with the test. As you're preparing for the test, I strongly encourage you to print one of these off. And then as you're practicing questions, have this there with you so that you kind of get used to where to find things and what's on there. And that will just be kind of more like practicing like the actual exam would be. So print that, and we'll start here in 4.3. And for section 4.3, we got definitions of logarithms. It's kind of a short little section. And we got properties of logarithms. They're all those ones that are sort of the inverse properties where we raise something to a log of the same base and we get the x out. And likewise, if we take the log of an exponential at the same base, we get back to x. We got change of base, and then just all these little definitions. So this first round of questions is just a bunch of little small questions that I'd have like 3 or 4 of them, kind of a part A, B, C, D sort of situation. So let me grab those. And so this first one, this one was log base 13 of 1. So what do I raise 13 to get 1? And that would be 0. Next one is log base 13 of 13. So what do I raise 13 to get 13? So that would be 1. And these properties are right here on the sheet, so you can absolutely check this out as you're doing them. This one we go log base 10. So root 10 I can write as 10 to the 1/2. And then we have a base and an exponential. The base of the log and the base of the exponential are the same. So it'll just be 1/2. You can also do it as a 4.5 where you bring the 1/2 down front and the log base 10 of 10 is 1. Either way we get a half. Here, so 7 to the 9th in a log base 7, it's just the 9. And the reason is 7 raised to the 9 is some big number, and this is what do I raise 7 to get that big number, and then the answer is right back to 9. And that's this one right here. Log, or 6 raised to log base 6 of 11, so that is this one, and so it's just going to be the 11. You kind of probably start seeing a theme here. E ln root 5, so if I rewrite that as E, actually, I don't even need to rewrite it. It's just going to be root 5. I was about to make that fancier, and that's pretty unnecessary because this is base E. These are both base E, so we're just going to get the root 5 back out. This one I'll get a little bit fancy. So here we got ln, and this I could do the whole subtraction thing, and then ln of 1. I can evaluate that minus ln e to the 4th. But maybe a little bit quicker, easier way, if you can see it, is if I have 4 downstairs, I can write that as e to the negative 4 and bring it up to the numerator. And then it's that ln of e to the e is going to just make negative 4. ln 1, that's like this one up here, that would be 0. And ln e is 1. So then in section 4.5, that's where we got kind of the meatier properties of logarithms. Remember, when we're multiplying, we are adding logarithms. When we're dividing, we can subtract logarithms. When we have a log to a power, we can bring that power down front. And these are those same definitions from 4.3. If the base and the argument of the log are the same, log base 10 of 10, that's 1. If the log of 1 will always be 0. A couple of other things that are helpful to remember in this section. If you have x to the 1/2, it's the same thing as root x. And writing a root x in terms of the 1/2 lets us use property 3, so that's where that's kind of an advantage. And then this one is x to the 1 over n is the nth root of x. So like for instance, x to the 1/3 is the third root of x. So a lot of times we'll see them like this in the problem, and it's much, much more helpful if we write them like that. And then lastly, x to the m over n, that's the same thing as x to the power over root. And so top number is going to be your power, bottom number is going to be your root. Okay, so there's kind of a problem on page 94. It's kind of an A through H one, where you're showing whether or not a property simplifies, a log simplifies down to something. I'm skipping that intentionally. I never used it on the test. I regret putting that page in there, and I just haven't gotten around to removing it yet from the packet because it messes up all my page numbers. So just ignore that, and then we're going to go on to problem 3. So these are those write as a single log type problems, and so this one is a kind of a big subtraction, so we'll just go log base 3, and then this would be my numerator because it's positive. There we go. And then this would be my denominator because of that negative, and when we're subtracting, that means we're dividing. And then from there, I can knock out a 5 pretty easily. So we'll go ahead and do that. And I can do that because it's factored, it's multiplying. And then I'm going to factor the denominator a little bit further, x plus 1, x minus 1. And then that's going to let me reduce that even more. So I wrote it as a single log, back on that first step. After this, it's just trying to simplify it. And so that would be my final. For this one, so this is a nice one to kind of show what the signs mean out in front of the log. So we're writing it as a single log. And one thing about that, so it sounds sarcastic, it is sarcastic actually, but only use the word log once in your answer for writing as a single log. Can't tell you how many times I see log, 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 log all over the place. So a single log, think just the one only log. These exponents, so they're coefficients, but we're going to bring them back up and have them be exponents. Anything with a negative on it came from the denominator, right? Because this would come out x to the negative third if I just brought that up, which means it should be 1 over x cubed. So negatives mean it came from the denominator, positives means it came from the numerator. So here I can just go y squared would be upstairs because it's positive. I'd have an x cubed downstairs because of the negative, and likewise a z to the 1/2 downstairs because it's negative. And this is a perfectly fine answer, but you can also write it x cubed and then square root z. Either one of those is completely acceptable. Okay, so now we're going the other direction. We're expanding the logarithm. And so this is where you have to remember some of that intermediate algebra. So cube root, I'm going to go, you can think of that as this way is probably easier. So y to the 12th, x7, z3, and then cube root I'm going to write as a 1/3 out there. And remember our properties of exponents is multiplies in. And so that would be log 12 over 3 would make y to the 4th. And then this will be 7/3. And then 1/3 of 3, so plain, oops, that was an x. Plain z right here. Pretend that says x. And now to expand, I'm just going to write each one of these gets its own log, and then the exponents become the coefficients. And then again, from the numerator would be positive, from the denominator would be negative. And that's, the reason for that is because I could write this. This is a good way to see how come the numerator has to be negative. If I rewrite this with just everything up in the numerator, I think I just said numerator, but I meant denominator. This is going to be negative 7/3 and then z to the negative 1. And if I use that addition property of logs for when they're multiplying, then everything just comes down front, and that's why these have the negative coefficients. So final answer on this is going to look like 4 log y, and then minus 7/3 log x, and then minus, I don't really need the 1, log z. This next one, a little less algebra in it than that last one. So I'm just going to treat this big square root here when I expand it as 3x plus 1 to the 1/2, and then over y. So I'll have a 5 ln x, and then I'm going to have a 1/2. I'll be positive because it's from the numerator. Ln 3x plus 1, and then a minus. I don't really need the 1 again, so ln y. Number 7 is going to involve a little bit of algebra. So again, we have this 1/3. So I'm going to treat this as log x squared y to the 8th, and then cube root with a square, so that'd be times the 1/3. So that'll be x to the 2/3, and then cube root of 6, 3 goes into 6 twice, so 2y's would come out of that, so y squared. I'm going to have to add the 2 and 2/3. The very slick way to do that is think of it as 2 and 2/3. And then if you remember back to somewhere in grade school where they taught us 3 times 2 is 6, plus 2 makes 8 thirds, and then we don't really have to even do we did the common denominator, but we were sneaky. So putting those together, I'm going to have log, and then this was 2 plus the 2/3 made the 8/3, so x to the 8/3, and then 8 and 2, so that makes 10y's. And now that I have it all kind of simplified and down to a single exponent, I'll expand it. So that'll be 8/3 log x, and then plus 10 log y. Okay, so next is section 4.6, and this was solving logarithmic and exponential equations. In the notes I have these kind of broken down into steps depending on what kind of equation you're looking at, because there's a few different flavors. I'm not going to kind of keep going back and forth between them. I'll just sort of go through the steps here. But you should look this over and kind of realize what the different flavors are and then what the plan is for each of them. Not the worst thing to write on an index card, a week before the test, and then just flip through that once a day, and by the time the test is around, you'll know them really well. Okay, so number 8 is we just have to be smarter than the 8 and the 4. I can use the like basis property, where I can write these both base 2, and then that will let me kind of dump the 2's and then set the exponents equal. So this is going to go 2 to the 3rd x minus 1, and it's 2 to the 3rd is 8, and then 2 squared 3x minus 2. And these are multiplying because they're both being raised to a power, so they're both raising this 2 to that power. Once I do that, then this gets really easy because I can dump those 2's, and I just set these two equal. So as I do that, I'll distribute. So 3x, and then 3 times 1, and 2 times 3 is 6x, and 2 times 2 minus 4. And then it's linear, so I want to get x's to one side, numbers to the other. So I'll bring my 3x over this way. I'll bring my 4 over this way. And that will give us, that dropped out, so that's a 1 equals 3x. And then the 4's dropped out. Divide the 3 over, and we get x equals 1/3. This next one, sadly, we cannot be smarter than the e and the 11. So we're going to have to use logarithms to solve this one, and that's what logarithms do, is they find exponents. So since it's a base e, I want to use natural log. So I'm going to natural log both sides of the equation. And then that allows me to use property 3 from the last section to bring this down in front. So now I get 2x plus 6 times ln e equals ln 11. But that's cool because ln e equals 1, so that piece drops out, and then I just have this to deal with. So 2x, I'm going to subtract the 6 over, equals ln 11, I should probably put parentheses, and then minus 6, and then I can just divide the 2, and that's it. So that's the exact answer, and then if I ask for the decimal, I got negative 1.8011 to 4 decimal places. Okay, for number 10, this one's going to be big. I'm going to have to write that on another piece of paper. So this is, I'm going to log both sides of this. And then that's where I get to bring my exponents down. So this is going to be x log 5 equals 4x plus 1 log 7. And then I got x's on both sides, so I'm going to need to get my x's together over on one side. So I think I will distribute that log 7 through. So that's going to let me move this x around. Right now it's all tied up in this. So this will be a 4x log 7, and then times 1, so log 7. And then next I'm going to get my x's over on one side, and then that's going to let me be sneaky and then factor the x out front, and then I can divide the rest of the stuff over. So I'm just going to do that on both sides. So then that would look like this. And then that's where now I have a common factor of x, so I can pull that out front. And then that leaves all this stuff behind. And then I'm just going to divide this on both sides, and for here I'm just going to do that, so I don't have to, you don't have to watch me rewrite it all twice. And so that would be our exact answer. And then if I wanted the to 10 decimal places, if I wanted it to 4 decimal places, x would equal negative 0.3152. Okay, number 11. So for this one, we can use the idea that if every term has a log, I can write it as log equals log, and then that's that kind of like basis property again, where then I can dump the logs and just set the arguments equal. So this one's a minus, so that's going to be x plus 9 over x minus 7 equals log 5. And then once I'm there, that's cool, so I have log a equals log b, which can only be true if a equals b, so I can dump these. And then that will leave me this. And then I want to get this fraction cleared, so I'm going to multiply both sides by x minus 7 to cancel over here, and then that applies it over here. So that'll be x plus 9 equals 5x minus 35. And let's see, I'm going to bring the x this way, and I'll add the 35 this way. So then I got 44, pardon, equals 4x, and then divide out the 4. And x equals 11. Okay, so for these ones we don't have everything with a log, we got logs and a number, and so our plan there is to write this as a single log, and then we can switch to exponential form and then solve from there. So this one's a minus again, so we're going to go log base 3 x plus 13 over x plus 1 equals 2. And so then this is the step that if people go wrong on this question, it's usually right here. So it's 3 and then raised to the second equals the stuff in the log. So 3 to the second makes that. And like kind of what people do is they remember the log disappears, so they just kind of disappear it and then set it equal to 2, which is like kind of not real math. So you want to do this instead. So here, 3 squared equals x plus 13, x plus 1. And then we're going to multiply both sides by x plus 1 to clear the fraction like on the last problem. And so that's really 9, so we'll go 9x plus 9. And that's going to cancel, leaving me x plus 13. And so I think I'm just going to do this one in my head. I'm going to bring the x over, and that's going to make an 8x. I'm going to subtract the 9 over, and that's going to make that be 4. And then dividing, I get 4 over 8, or 1/2. This next one's similar, except now it's an addition. So that'll be log base 6x, x plus 5 equals 2. And then there's that same thing. We're going to go 6 raised to the second equals this stuff. So 6 squared makes x squared plus 5x. And I'm going to subtract the 36 over. And I'm doing that because this is quadratic, so when we have a quadratic, we want to get it to 0, so we could try to factor it, or maybe quadratic formula, but on these ones, they've all factored. So 0 equals x squared plus 5x. That'll be a minus 36 when I bring that over. 0 equals x. And then we need two numbers to multiply to be negative 36 and add to be positive 5. So plus 9 and minus, excuse me, 4. And so x could be negative 9 or x could be 4. And then that brings me to the thing that I keep forgetting to say at the end of every problem and remembering after I start the next one. We should be checking solutions on these. And so far they've all checked. If I put the 1/2 in here, this whole thing stays positive. We don't have to check and see if it really makes what we're saying, that it's going to make a 9. You can, but we do have to check for extraneous solutions. And over here, this time we got one. Because remember, we can't, if you think of our log graph, it looks like that, right? We can't put negative numbers into logs. They're not defined. And so I got a negative that I'm trying to put into the log, so that one's no good. If I put 4 in, it keeps both these positive. So that's the only real answer. And on these kind, it can be that they both work, that neither one works, or that one works. And it just depends on the geometry. Because, a log graph basically looks like this. This thing is a parabola, so it could come down and only cross it once. It could cross it twice, or it could never cross it. So just sort of the geometry behind the algebra. Okay, that brings us to everyone's favorite section, exponential models. And so you do get this on the test, so it just sort of is defining the pieces of the formula. So remember, A naught is our initial value. It's whatever our starting amount is. E is E, 2.718, etc. R is the rate, and T is time elapsed since this amount was there. So let me do some examples. Okay, so this wouldn't be on the test. This is just kind of like how I organize myself when I'm setting these up. If you have something different that works for you, you certainly don't have to show this. So the half-life of an element is 540 years. If the initial sample contained 200 milligrams, how much of the element would we expect to find after 1,500 years? Okay, so they told us that our initial amount is 200 milligrams, and the time is going to be 1,500 years. That's what we're trying to find, is the amount that will give us at this time. And then they gave us this half-life thing. So that means in 540 years, we would have, if we started with 200, we'd have 100. So this one gives us our rate, because we have this ordered pair that we can plug in and then use that to find R. And then once we get our R, then we can have our equation, and we can plug in this T and use that to find the final amount. So here this is our this side of the equation. So 100 equals 200 is our initial, this is our output, this is our input. E to the R is what we're trying to work out, and then T was 540. I'll divide that 200 over because that will make it a little bit better. And that gets me 0.5 equals E R, and then 540. And then this is where we do the thing with the natural log both sides, because that lets me get at that exponent. So I'm going to ln here, natural log all that. Natural log of 0.5 equals, so this becomes 540R, and then ln E, but ln E is 1, so that drops out. Divide this over, and then that makes R. And in the last video on this, that's the thing that I was calling big R, so they didn't have to write this over and over. I'll just use big R to stand for that. And then this one isn't too bad because now that we have R and they gave us time, we're just plugging into the formula. And so the amount after 1,500 years, the amount final, is going to be the amount initial, and then E to this value right here, this, which I'll just represent as R, and then 1,500. So then I just did, ln of 0.5 divided by this times 1,500, and then raised E to that and times 200. And I got about 29.16 milligrams would be left. Number 15, find the time required for an investment of $10,000 to grow to $15,500 at an interest rate of 9% per year, compounded continuously. So continuously, the formula is, it's the same one we've been using, just with different letters. You may know it as A equals PE to the RT. It's the same formula as what we're doing. So this is like our initial amount. This would be our final amount. They gave us R, and we're trying to find the time, so we're looking for T. So our final amount is 1,500 or 15,500. Initial was 10,000. E, R is 0.9, and then T. And then with that, I'm gonna divide over this 10,000. And then those cancel, and that's going to be 1.55 equals E 0.09 T. And then here I'll natural log both sides. It's just kind of that same solve over and over. Bring the exponent down. Ln E is 1, so that drops out. And I just have to divide over the 0.09. And then that gets me T. And when I put this in the calculator, I got about 4.87 years. Number 16, only 60% of the carbon-14 in a fossil remains. How old is a fossil? Round to the nearest year. The half-life of carbon-14 is 5,730 years. So on this one, they didn't give us an initial amount, so that's where we just pick an easy number, and I pick 100. And so then if 60% remains, then that means my amount final will be 60. And they told me the half-life, so that means at 5,730 years, I would have 50 grams or whatever this is left. And so what we're trying to do is figure out how long it is till that would take to have 60%. So we're going to go and use this to find our rate. So 50 equals 100 E R to the that. And you can also just jump straight to the 0.5 if you don't want to do that out. Some people like to have the numbers. Some people are comfortable just doing that. Here I'm going to natural log both sides. That allows the exponent to come in front again. And this whole solve gets very repetitive after a while. And then ln e again is 1, so that drops out. I can divide that over. And so that cancels. And so that's r, so again I'm going to call that big R just so I don't have to write that. And so then I know there's going to be, we're trying to figure out how long it will take for 60% until there's only 60% left. So we'll go 60 equals 100. You can also jump straight to the 0.6. E, big R, and now I know that quantity t. So divide the 100, boom, and we got 0.6 equals E and RT, again with the natural log. Bring the RT down front. And then divide that R over. And then remember, R is this thing right up here. So if this was here, it would just flip over and the 5730 would be on top and the ln 0.5 would be downstairs. And then just chunk all that in the calculator, and I got t to be about 4,223 years. Number 17. So in 1985, the population of the Earth was 4 billion people. In 2015, the population of the Earth was 7.125 billion people. In what year will the population reach 10 billion? So what we're going to do is let 1985 equal, let that be t equals 0. And so if I do that, what that means is the 4 billion people is my A naught. It's my starting amount. And then I can use the 2015 and 7.125 as my order pair to get my rate. And 2015 is 30 years past 1985, so we'll do 30 and then 7.125. The amount final, that's going to be 10 billion, and we're looking for the time that will happen. So first thing, we're going to find our rate again, and this one is slightly different. 7.125, actually it really isn't, it's just that it's a 4, they're not nice numbers. E to the R, and then that happens at 30 years. And so I'll divide the 4 over, and then this makes an ugly number to write out, that, and that equals E to the R times 30. And then we'll do the natural log thing again. So we'll natural log both sides. And then since that's not that great to write out, I'm just going to say verbally, I'd bring this down. E is 1 again, divide over the 30. And then that'll give me a big R of ln 1.78125 over 30. And once I have that, then I can use big R and then 10 to find the t that it would happen at. So we got 10 equals starting amount 4, E, and then big R we know t. So divide the 4, and that'll go 2.5 times E to the RT, natural log, and this comes down. Ln E equals 1, so we divide out R, and just chunk that in the calculator, and you should get t equals about 47.6. So 1985 plus 47, so 2302. So that would be 2032. Section 3.2 is quadratic functions, and this is where we picked up standard form and vertex form. I'll kind of go through all this as I do examples, but this is on your sheet of notes for the test if you're in my class. Okay, so for this first example, we're supposed to write the quadratic in this form. So I'll go ahead and use the x equals negative b over 2a, and use that to get the x-coordinate of the vertex. So negative of negative 6 over 2 times 1. So that's going to make this be 3 over 2, or 6 over 2, so that'll be a 3. Once I know this, I can plug it back in and get the y. So y will equal 3 squared minus 6 times 3 plus 4. 9 minus 18 plus 4 should be negative 5. And so that puts our vertex just up here at 3, negative 5. So let's see, I think we just had to write it in the form of the graph. So that's going to be y equals, and a we know is 1 because there's nothing in front of x. So that becomes x and then minus 3, because the minus in the formula, and then plus k, and k is negative 5. And then graphing, this is going back to our 1.5 transformations. So x is 3, y is negative 5, so that'd be right here. And I'll just do the over 1 up 1, over 1 up 3 thing that I did back in transformations in 1.5. And that gets me the rest of the parabola. Okay, so this one, all kinds of questions. So we'll do vertex first. So I'll do x equals negative b over 2a again. So I think that will do that right there. So that's going to be negative b will be negative 8 over 2 times negative 2. So double negatives will be positive, and 8 over 4 makes 2. And then the y-coordinate, I would just plug 2 back in here and get negative 2, 2 squared plus 8 times 2, and then minus 4. So that'll be negative 8 minus 4 would be minus 12, plus 16 should be 4. So my vertex is 2, 4. Axis of symmetry always matches the vertex, so that would be x equals, and it should be in the form of an equation, 2. Let's see, the x-intercepts I have to do a little bit of work to get to. This I'm going to set this to 0. I need more space. So I'm going to do that on some scratch paper over here so I don't run out of room. So that'll be negative 2x squared plus 8x minus 4 equals 0. I don't love the negative leading terms, so I'm going to just multiply everything by negative 1. And that's just to make the numbers a little bit friendlier to work with. Actually, you know what I'll do instead? I'm going to divide by negative 2. That looks better. Because everything's divisible. So I can knock out a factor of 2 also. So that's going to be x squared minus 4x. 2 goes in there twice. Equals 0. I could have also done that as a common factor after I multiplied by negative 1. So now that I have that, I can either complete the square or use a quadratic formula. For me, I would prefer to complete the square because a is 1 and b is even, but you can also do this by the quadratic formula. So x squared minus 4x, and then I'll shoot the 2 over to this side. And then this is where we go half of 4 is 2, and then squared makes 4. And I can factor. And this side would be a 2. Rooting both sides, I get x minus 2 equals plus or minus square root 2, and then bring the 2 over. And so my x-intercepts are going to be at 2 plus or minus root 2 comma 0. For the y-intercept, I just have to let x equal 0. And so when I do that, I get -4. So 0, -4, because all this stuff drops out. And all that will be easier with the graph. So we'll do our vertex is at 2, 4. And it has a stretch of 2 on it, and it's negative, so it's opening down. So it's going to go over 1, down 2, over 1, down 2. And then we have the y-intercept at -4. And then that lets me kind of draw on the rest of this. And then the x-intercepts, root 2 is about 1.4. So 2 minus 1.4 should be about 0.6. So that's that one. And then 2 plus root 2, that'd be about 3.6. And that's that one. Domain for these is all real. It's -infinity to infinity. Range goes from -infinity up to the 4. It includes it. It's increasing. So there's my axis of symmetry. And it's increasing on the left-hand side, decreasing on the right. So -infinity to 2 for increasing, and 2 to infinity for decreasing. And remember, increasing, decreasing, always get parentheses. And I think that's it on that one. Okay, 3.4 is graphing polynomial functions. This one has a graphing supplement. If you have not tried that, you should, to make sure that you're ready for the test. Anytime I do a graphing supplement, it's because I don't think the computer does an adequate job of basically giving you examples for graphing, and it's hard to graph on a computer. So they'll have like a supplement with them in the folder above the calendar, and you should check those out, because how they look on there is how they're going to look on the exam. So for graphing polynomial functions, this is the thing where you have to remember we have kind of two things. We have the cross bounce at the intercepts. Remember, even powers bounce, odd powers cross. And then we had those 4 pictures. We had positive, even. We had negative, even. And then we have positive, odd. And negative, odd. And we saw those back in 3.3. 3.3 didn't really have much in it other than this. And it gets picked up in 3.4, so not covering 3.3. And so what we do is we count up, in this case, we can look at our leading coefficient, or if it's factored for us, so we can count up our x's and figure out which of these it is. So I have a negative, I have 1, 2 right there, 3, 4 x's. So negative x to the 4th, so this should come out being negative even. I have x-intercepts at -5, 1, and 5. And this is going to bounce, cross, cross. So -5 would be there, 1 is here, and 5 is out there. So it's going to come in from the bottom, bounce off of the -5, cross on the 1, and cross on the 5. Again, these points, we don't know how high or low to make those because we don't know Calc 1 yet. So for our purposes, just draw something that's clear and I can tell what it is you intended with it. This one's similar. So we have negative and 1, 2, 3, 4, 5 x's. So this is negative odd. So it should end up looking kind of like that. The x out front is x equals 0, and that's a bounce. We have x equals 3, that one's a cross. And x equals 6, and that one is a bounce. So 0, 3, and 6. And this one's going to come in from the top. It's going to bounce off of 0. And then it's going to cross on the 3 and bounce off of the 6. And that would be that. For this one, we're given the graph and asked to find the equation. And the assumption is all the multiplices are either 1 or 2. So if we see it bouncing, it's 2. If we see it crossing, it's 1. And then we have that constant out front that we're going to have to find. So this is going to set up as y equals a, and that's that constant that we're going to use the y-intercept to find. Our first point would be x plus 1, and that's going to be squared because it's bouncing. And then 2 is crossing and 4 is crossing. So x minus 2 and x minus 4. Remember, the factors and zeros always have opposite signs. Once I do that, then I have kind of my template set up. So I'm going to let, this is just an xy here, so I'll let y equal -2. A is what I'm trying to work out. If I let all these x's be 0, this will just be 1 squared times -2 times -4. So that's -2 equals, it'll be 8a, and then dividing, I get a equals -2/8 or -1/4. And so then writing the final answer will be y equals -1/4 x plus 1 squared, x minus 2, and x minus 4. 3.7 was graphing rational functions, and this one's a little bit challenging. So there's a lot of steps to getting it done. You'll see when I get to the questions that are graphing on this, within the directions, I'm basically asking you to do all these steps and to note that information. So you don't really have to have this memorized, because the prompt in the question is going to kind of walk you through what things you should be finding. Just kind of go through them. So to graph a rational equation, we're going to factor the numerator denominator and see if it reduces. And if it does, then that means there's a hole in it. If not, then we can kind of proceed. The domain is going to be whatever makes the denominator 0. Once we've written it in lowest terms, and the domain is based on the pre-reduced version, not if it needs reducing. So we'll write in lowest terms, and then we'll find x and y intercepts. To find x-intercepts, let the numerator equal 0, because remember, when we multiply with that denominator, it just gets canceled out anyhow. And then find the y-intercept, we just let x equal 0. Vertical asymptotes, that's set the denominator to 0 and solve, and that will often match the domain unless there's something that reduces out. And then we find the horizontal or oblique asymptotes, and that's the thing where we have small over big, where if we have like x over x squared as our leading terms, it's going to be y equals 0. If we have something that's same, so x squared over x squared like that, that would be the ratio of the leading coefficients. For that one, it would be y equals 1. And big over small means we have to long divide to get the oblique. And then the last thing we want to do is check and see if the horizontal or oblique is intersected, because that eliminates a lot of possibilities when we're graphing. So this first question is just an asymptote question. And this is asking us to find all the vertical and horizontal asymptotes. So looking at A, for the horizontal, it's going to be y equals 0, because this is small over big. And then for the vertical asymptotes, we let the denominator equal 0. And that'll be x plus 3, x minus 3 equals 0. So we have verticals at x equals negative or positive 3. For this one, it's same, so our horizontal is going to be the ratio of the leading coefficients, so y equals 3. And then for the verticals, x squared plus 6x plus 8 equals 0. That'll be x plus 2, x plus 4 equals 0, so x equals -2 or -4. This one is big over small, so that means we have to do long division. You can also use synthetic if you know it. So x squared plus 8x minus 14. So what do I multiply x by to get x squared? Would be x times x squared, x times 3, 3x. And then this becomes 5x minus 14. And then what do I multiply x by to make 5x? That'd be a plus 5. And I could really stop there, because the rest of this will just be remainder, and the remainder goes to 0. So the oblique, or I think this book calls them slant asymptotes, will be y equals x plus 5. And then since the denominator is x plus 3, we'll have, so that's our oblique. And then our vertical will be x equals -3. Okay, so then we're graphing these, so I'll just kind of go through the steps. Step 1, identify the domain. So I'll go ahead and factor this. So x minus 2, x plus 1. And so our domain will be that x isn't 2 or -1. Next up is find the X and Y intercepts. So x-intercept is just the denominator set to 0, so that'll just be x plus 3 equals 0, so x equals negative 3, and so that gives us the point negative 3, 0. For our y-intercept, that's where we let the x's be 0, so that's going to be negative 3 halves from right here on the ends. So 0 and negative 3 halves. Find the vertical asymptote. Okay, so the vertical is going to be where the domain messes up. So that one will be x equals 2 or negative 1. The horizontal asymptote, this is small over big, so it's going to be y equals 0. Step 5 is the horizontal or oblique asymptote intersected. If so, where? So horizontal asymptote is y equals 0, and it's intercepted at the right there at the x-intercept, so that's going to be the only spot. And then after that, we're graphing. So let me get my asymptotes drawn in. So I have verticals at negative 1 and at 2. And then we have a horizontal one at x equals 0, which is the y-axis. And then we can get our intercepts. So we have a y-intercept at negative 3 halves. So that'd be about there. And we have an x-intercept at negative 3. So that would be about here. And then from that, we can get the graph. So let me bring this one back. And there's this thing with the vertical asymptotes. So if they are going off together, it had to have come from an x squared. If they're going off in the opposite directions, then that means the multiplicity was 1, and it'll look like 1 over x. So if we have a square in our denominator, we can expect them to go the same way. If everything's linear in the denominator, we can expect them to diverge like that. The other thing is that the intercepts, if it's a x squared in the numerator, it's going to bounce. If it's a x to the first in the numerator, it's going to cross, or an odd power, even power. So for this one, let's see, we know that we cannot cross the horizontal asymptote except right here. This is already below the asymptote, and so the only thing it can do is stay there. So this piece has to do something like that. Since these are both to the first, and this is going down, I know this side has to be going up, and I know this side has to be going up. I know my asymptote is crossed right here. There's no squares, so there's no bouncing. So that means it's going to kind of come down and then come back up, and then approach that asymptote as it goes to negative infinity. And then for this side, it has to do something of that nature. Same thing, same directions, just another example. So I'll get this factored and get x plus 3, x minus 1. And then for the denominator, that's going to be x plus 2, x minus 2. Nothing reduces, so domain is just going to be x can't be plus or minus 2. X-intercepts, right there in the numerator, so negative 3, 0, and 1, 0. Y-intercept, that's that on the end if I let all the x's equal 0, so double negative, so that'll be a positive 3/4. Vertical asymptotes come from the denominator. So x equals plus or minus 2 matches the domain if there's no reduction. Horizontal, this is same, so it's going to be the ratio of the leading coefficients, which is just 1. And then we need to see if this is crossed, so we'll do x squared plus 2x minus 3, x squared minus 4 equals 1. So I'm just saying the function equal to horizontal and then seeing if there's a solution. So I'm going to multiply both sides by x squared minus 4 to clear the fraction. and I get x squared plus 2x minus 3 equals x squared minus 4. If I bring the x squared over, it drops out, so I'll just cancel those. So instead I'll bring this 3 this way, and I get 2x equals negative 1, or x equals negative 1/2. So that means that we cross at x is negative 1/2, and then the y is the asymptote, so y was 1. So now we got all our stuff, and then we just have to draw it. So we got verticals on the 2's. Horizontal at 1. And then I'll get my intercepts graphed. So we got 3/4 for the y one, so that'd be just below there. We have -3 right here and 1 right there. And we know our asymptote is crossed at negative 1/2, 1. So negative 1/2, 1 would be right about there. And this isn't any sort of bounce cross situation, it's just a matter of can the graph go through there, and it does. So what that tells me is, and it can't come back around where I had found another place it crosses. So this has to come in from the top and then look something like that. This one's below, it can't get above here because this is the only place it crosses. Plus this is to the first, so these have to diverge. So this side's going to infinity and this side's going to negative infinity. And then, let's see, there was no squares down here, so we'd expect them to go opposite directions. So this one has to be going up since this one's going down. So that means it's going to do something like that. And then these next two are, here's the graph, and then from that, figure out the equation. So, and these are the ones where all this stuff is pretty helpful. So we know the verticals are going to give us the denominator, the x-intercepts are going to give us the numerator, and then we'll know the powers of those things based on the behavior. So bouncing is squared, going off together is squared for the denominator, crossing in the numerators to the first, and likewise to the first if they're going off opposite directions. So let's figure out what we got. We're going to have y equals, we need that constant for a again that we're going to end up figuring out from the y-intercept. My one x-intercept is at 1, so that means I have an x minus 1, and it is to the first because it's crossing. Downstairs I have vertical asymptotes on -2 and 2, so I'll be x plus 2, x minus 2. And I know those are to the first because these are diverging, as is this side. With that, then I can plug in my y-intercept and use that to get a. So we know it's at 0, 1, so y is 1 when x is 0, so I'll be a -1, 2, -2. So that would look like 1 equals, we got 2 signs, so it's going to be positive a over 4, and multiplying up, that means that a equals 4. So my equation is y equals 4, x minus 1, x plus 2, x minus 2. Number 27 is about the same idea. For this one, a little bit more complicated. We have a little bit different behavior going on. So let's get the template set up. We're going to have a, we have an x-intercept at -2, so I'll be a plus 2 as a factor, and it's going to be to the first because it's crossing. We have another one here at 3, so that'll be an x minus 3, and that one's going to be squared because it's bouncing. For the denominator, vertical asymptotes, I have one at -1 and one at 4. So x plus 1, and this one is going to be square because those are heading off together, and this one's going to be to the first because they're diverging. This side goes down and this side goes up. And then once I have all that, then I can use the y-intercept at -3 there and just plug that in for the x's, or sorry, for y, and then 0 for x, and then solve. So the y is negative 3, a is what we're trying to work out. So this will be 2, negative 3, 1 squared times negative 4. And let's see if I clean all that up. I have a double negative, so it'll end up positive. And this is going to be 6. Oops, I dropped a square. There it is. So it'll be 9 times 2 is 18 over 1 squared times 4 will be 4. And I think rather than reduce, I'm just going to multiply both sides by the 18 because it's going to work well with that 3. So 4 over 18, just using a reciprocal. And then the 3 goes in 6 times. So this is negative 4/6 or negative 2/3. Actually, let's see. I just figured out where my sign was. This was squared, so sorry, that should have been negative, so that's negative and that's negative. And now this is positive. There we go. And so then writing down my answer, 2/3 up in the numerator looks funny, so I'm going to write it as y equals 2/3, and then x plus 2, x minus 3, and x plus 1. Yeah, if we have the fraction up here, then we have a fraction and a fraction. That's not considered simplified. So that'd be the form of the final answer. Okay, section 3x. This is our inequalities. And so we had 3 methods for solving these. We had graphing, test points, and sign chart. So for the polynomial ones, I prefer graphing, so that's how I'm going to show it. This would be, if I graph this, x equals 0, x equals negative 4, and x equals 4. And this is going to bounce, bounce, and cross. So if I just draw kind of not a great graph, so I'll just make that one negative 4, 0. I'll call that 4. And this will be 2, 3, 4, 5 x's, x to the 5th. Should look kind of like that. So we're going to come into the negative 4 and bounce. We're going to bounce off the 0. And then we're going to cross on the 4. And then from there, we just have to figure out what we're looking for. We want the greater than or equal to zeros. So I have these 3 negative regions, but I'm going to have to be a little careful because I also have some zeros there that I have to account for. And I only have that one positive region over there. So for things that are either positive or 0, my solution set's going to be negative 4, 0. Union that, and when we're just doing a single number, we use the braces in interval notation. This one would be 0. Union that with from 4 to infinity. So that one, we have x equals 0 bounce, x equals negative 4 cross, and x equals positive 1 cross. And we got 2, 3, 4, and a negative. So negative x to the 4th should look like this. So we'll do it like that. I'll call that one negative 4. I'll call that one 1. So there's our intercepts. We're going to come in from the bottom and cross at negative 4, bounce off of the 0, and then cross back at 1. And for this one, we want the less than or equal to zeros. So this is negative here. This would be a positive and positive, negative. And we want to make sure we catch that 0 right there. So our solution is going to be negative infinity up to negative 4, bracket, because we're including zeros. 0 is a 0, so we got to get that one in there. And then from 1 to infinity. Okay, and then these last 2 are rational, so those ones I'm going to do a sign chart. You could also do test points. I would recommend graphing. Graphing's a hard way to, the graphing would be like the last section. So I think probably either test points or a sign chart are going to be quicker. So first thing we'll do is get this factored so we can see what we got. So that's going to be x, let's see, minus 5, and x plus 1. And then this one is a little bit sneaky, it's just x plus 4. Looking for greater than or equal to 0. So for a sign chart, I'm going to go ahead and go x minus 5, x plus 1, x plus 4. Do like that. And so I have 0 at negative 4. I have 0 at negative 1. I have 0 at 0. And I have 1 at 5. And so these two are going to be undefined. And then this one. And at negative 1, these ones are actual zeros. These are from the numerator. And 5. So, you do this, just try to make it a little clearer. And then as long as we have positive x's, it's going to fill in negative on this side. Like you can try a test point if you want to convince yourself. If x was 4, 4 minus 5 would be negative 1, so that's negative. It'll pass through 0 and become positive. So I'm just going to do the quick version of filling this in, because it's going to go negative 0, positive, negative 0, positive, same here. And then you don't have to draw the graph on here. I like to, it just kind of helps me get the interval notation right. We do have to go 4 negatives makes a positive here, 3 negatives makes negative, 2 negatives would be positive, 1 negative, negative, and we have all positives. And we want greater than or equal to 0, so we want the positive regions. That's going to be there, in between here, and going this way. And then endpoints, undefined, so that would be open, 0 would be solid, undefined open, and then 0 solid. So if I translate that to interval notation, negative infinity to negative 4, the parenthesis, negative 1 to 0, and then solid there, so union 5 to infinity. Last one, so this is going to go x minus 2, x minus 2. So let me write that as x minus 2 squared. I could also write two separate factors into two separate lines and get the same answer over, that'll be x plus 3, x minus 3 less than or equal to 0. So x minus 2 squared, x plus 3, x minus 3. So we got a 0 at negative 3, that's actually an undefined. We have a 0 at 2, that one's an actual 0, and a 0 at 3, and that one is undefined. And then we'll just do that just to make it a little tidier. So this one, if you'd done two factors, you would get double negative on this side, double positive, and it'll always be positive because of that double negative. We've written with the squared, you know something square is always positive. This would come down, it would bounce off at 2 and come back up for a parabola, so it never drops below the axis. So the only thing that ends up contributing is a 0. And then these ones behave, so they are negative, positive, 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 negative, negative, positive. So 2 negatives make a positive, 1 negative, negative, 1 negative, negative, and positive. And we want the less than or equal to zeros. And so we want to not include those endpoints. We want the negative regions, and we don't want the undefines. We do want the 0 in the middle, so this will just end up being continuous. So my solution is going to be from negative 3 to 3. And that concludes the exam 2 review.